So I guess we should get started. And really the goal of this talk is really just to describe how there's this sort of wonderful overlap or synergy between domain-driven design and the microservice architecture. And it turns out there's actually overlap in a couple of different ways, both in terms of strategic domain-driven design and bounded contexts, and then what I'm going to talk about today, namely aggregates, one of the building blocks of DDD. So that's sort of the goal, and kind of the big message is that, you know, if you're developing applications with the microservice architecture, you really should go study domain-driven design because they work together really, really well. So a little bit about me. So I live just up the road in Oakland. And I got my start in programming a really long time ago, mid to late 80s, building Lisp systems. Everything from compilers, garbage collectors, all the way up to IDEs. And then eventually programmed in Java, and my book, Pojos in Action, came out 10 plus years ago. And sometime shortly after that, I started tinkering around with Amazon EC2 right at the early days of cloud computing, and ended up creating a startup called Cloud Foundry, which was acquired by SpringSource back in 2009, shortly before SpringSource was acquired by VMware. And so I was there for a number of years, and now today I pretty much sort of focus on the microservice architecture. You know, back when I was working at VMware, just sort of got interested in what ultimately was known as the microservice architecture, because there was a lot of synergy between paths like Cloud Foundry and the microservice architecture and sort of enterprise application development. And that just kind of sent me down this microservice architecture route. So I do consulting and training around that, and I also have a startup, and we're building a platform to simplify the development of business applications that use the microservice architecture. And, you know, 10 years have gone by, so I've recovered from the trauma of writing my first book, and I'm working on another one, this time on the microservice architecture. And if you go to learnmicroservices.io after the talk, that page is really a collection of links to a whole bunch of resources that you can use to learn more about the microservice architecture. So that's me. The agenda, so I'm going to just sort of talk about some of the problems with domain models, sort of how we traditionally build business logic in an enterprise application, and the microservice architecture. There's sort of a conflict there. Then I'm going to describe how aggregates can solve that problem, and then talk about some of the other issues, specifically around how to do transactions. In other words, how to maintain data consistency in a microservice architecture, and we look at sort of an event-driven way to accomplish that. Okay, so let's get started. So that, you know, big idea with the microservice architecture is that it really is a form of modularity. You know, we're building systems that are more and more complex, and, you know, the standard way of dealing with complexity is to modularize it. So there's a division of knowledge and a division of labor. And at sort of a lowish level, you know, say if you were in the last talk, which I actually wasn't here for, but I'm guessing it was about Java 9 modules, that is one form of modularity. And then the microservice architecture takes it to a different level, where the high-level modules in your system are, in fact, services. And each service corresponds to a business capability, or in other words, a business function. So instead of building an application that consists of a single executable or deployable unit, you are building a system that consists of a set of services, each service performing a particular business function. So you end up with an architecture that looks like this. It turns out lots of moving parts. But the key part of this is that your business logic is now implemented by a set of services which can be independently developed, deployed, or tested, deployed, and scaled. And then in order to ensure that those services are loosely coupled, each service has its own private database. And the reason for that is, well, if you're a developer and you're working on your service and you want to change your database's schema, you really want to be able to do that without having to coordinate any schema changes with anyone else, because as soon as you have to coordinate across an organization or outside of your team, then you're going to be slowed down because you have to schedule that schema change with the development needs of other teams who are working on different timelines, different priorities, and so on. So it really slows you down. So in other words, you cannot share data. And that's really, really important. It enables you to much more effectively parallelize development. But that actually creates a whole bunch of problems. And one of the problems just in general with the microservice architecture is, well, if you think about your domain model, right, it is a tangled web of classes. In traditional object-oriented design, just classes are just referencing other classes, whether through associations or hazard relationships, etc. So an order has line items and it has an address, it references a customer, the line items reference a product, and that's just sort of a typical domain model. The challenge, however, is that, well, I want to partition that domain model, put orders in an order service, customers in a customer service, and products in a product service. But how does that fit with my domain model? Because now there are relationships that span service boundaries. And given that a relationship is really an object reference, how do you have these object references span boundaries? And so, it's like our traditional object-oriented modeling approach doesn't exactly fit with the microservice architecture. And then another challenge really comes from the fact that the data is partitioned across multiple databases, or at least encapsulated within services, and one service cannot access another service's data. And we pretty much rely on transactions and sort of access arbitrary pieces of data in order to enforce business rules or invariants within our system, or in other words, to maintain data consistency. So let's imagine that in this online store example, there's a business rule that says that a customer has a credit limit, which means that in order to, when we're placing an order, we have to make sure that that new order will not violate the customer's credit limit. And in a traditional monolithic application, it's straightforward, right? You begin a transaction, you find the existing orders, you find the credit limit for the customer, and you make sure that this new order will not exceed the credit limit, and then you create the new order in the database, and then you commit the transaction. Even if we're programming in JPA, underneath, this is roughly the sequence of SQL statements that will get executed. And what's really nice about this is that one of the key properties of ACID transactions is that if there are multiple simultaneous transactions trying to create orders for the same customer, they will basically be serialized. They will be, through locking or whatever mechanism the database uses, they will be executed one after the other. And so our business rule will be maintained. And that's sort of, we just take this for granted. This is sort of like oxygen from a perspective of an enterprise developer, that we've got transactions that will enforce data consistency. But if you reinterpret this database transaction in the context of the microservice architecture, there are some clear problems. Number one, orders and customers are actually belonging to different services, and we can't write a transaction that simply accesses the order table and the customer table. Also, even if we did, we would need a distributed transaction because we're now spanning services and potentially spanning multiple databases as well. So there's sort of a mismatch between sort of our typical transactions and how we and how they would work in a microservice architecture. And this is particularly problematic because basically two-phase commit is not a viable technology option today. Because on the one hand, it sort of works, but there's sort of a whole bunch of kind of theoretical and practical reasons why two-phase commit is not a good choice. It impacts the availability of your system just from a practical point of view. Another really practical concern is many modern technologies, modern sort of NoSQL databases and modern message brokers don't support two-phase commit. So you can't actually use it. And then there's also the CAP theorem that says you basically have to choose between a consistency and availability, and people prefer availability over consistency. So for this reason, modern sort of web-scale applications simply don't use distributed transactions. And then also, even ACID transactions just don't fit with the typical NoSQL database transaction model. You can normally in a NoSQL database, you can only update one thing, one document, one row, one key value pair. And so the traditional enterprise model of beginning a transaction, updating multiple things, just does not fit with the underlying technology stack. So we have a problem. So it turns out that one solution to this problem comes from domain-driven design. Just out of interest, who here has read one of the DDD books? Okay. So, what's fascinating about it is this book came out in like 2003, 2004. So it's sort of a, computer history sense, it's a relatively ancient text, right? And the other thing that's really fascinating about it is that it sort of, the whole motivations for domain-driven design are sort of deeply philosophical. So there's a certain irony that we've sort of got this philosophically motivated ancient text that's incredibly useful for building modern software based on the microservice architecture and NoSQL databases. But it really is true. So one of the the key topics in DDD is that there's these notion of building blocks, which are really roles that classes play, as well as sort of the the characteristics of classes in your domain model. So we have entities, right, which are objects that have a persistent ID. There are value objects that are collections of just sort of attributes, and they can just be used interchangeably. They're immutable, and they tend to be used. They can be used interchangeably. And we've got services that contain business logic that doesn't belong in an entity or a value object. And then there are repositories that basically are an API for retrieving entities from the database. And almost all of those four terms should be familiar to everyone in the room, right? They're terms from JPA, and they're also terms from, well, I suppose like the Spring Framework, for example. So the first four of those have been used have just become standard terminology for developers. But then there's this fifth one known as an aggregate. And when I read, DDD book, however many years ago, I just ignored it. Didn't really solve any problems that I was having, because I was building monolithic systems on top of a single relational database. But it turns out that aggregates actually are this really important concept that are incredibly useful when you're developing microservices. And the idea of an aggregate is really simple. I mean, we have in fact been using aggregates since the beginning of time. We just haven't had a label for the concept. And an aggregate is a cluster of objects that can be treated as a single unit. And it's a graph consisting of a root entity and one or more other entities or value objects. And in fact, most of business entities or domain or things that from our business domain almost always are aggregates. So if you think about an order, that there is more to an order than just the order class. There's the order line items. There's the address. There could be the payment information as well. And collectively, that little cluster of objects forms this sort of business entity known as an order, and it is an aggregate. And so it's just sort of like this idea of kind of grouping objects or grouping classes in your domain model into these chunks that you can just treat as a single unit. So that's just kind of useful in a conceptual sense. But then there's some rules that aggregates have to conform to that are actually incredibly useful when you're building modern applications. And one of those rules, which at first glance seems very strange, but it's the rule that says references between aggregates are in terms of identity. So they're in terms of primary key. So in other words, an order doesn't have an object reference to a customer. It just has the customer ID. Likewise, an order line item doesn't have an object reference to a product. It just has the product ID. And and this is really interesting because from the perspective of sort of classical object-oriented design, this would be considered a smell, right? You should not have foreign keys, which are a database concept, in your domain model. But it turns out that this is really, really useful. I mean, among other things, it actually clearly defines what is part of an aggregate because it's reachable through an object reference versus what is outside the aggregate, where there is no object references. So our aggregates are very are now these self-contained chunks with very weak references between them. So any reference from one aggregate to another is purely by ID, as opposed to an object reference. And with that, it's then very straightforward to partition your domain model into multiple services. You can put different aggregates in different services without having to deal with object references attempting to span services. So the order has a reference to a customer that's in another service, but it's just in terms of an ID, and that's quite okay. So quite interesting for some sort of ancient book. And then the other rule that aggregates have to conform to is that one transaction can only create or update a single aggregate. So in other words, our transactions end up being very sort of fine-grained. And in fact, the original motivation for aggregates was, if you go read the DDD book, is sort of as a consistency boundary, which kind of just never made sense to me at the time because I was building applications where I could begin a transaction, update whatever I wanted, and then commit the transaction. So I didn't see the need for this aggregate concept. But then when you go look at what happens in a microservice architecture where you cannot use distributed transactions and you have to limit the scope of a transaction to fit within a service, this rule means that if you think of a service as containing one or more aggregates, then the rule that says a transaction can only create or update a single aggregate will therefore guarantee that the transaction fits within a service boundary. So it's sort of like DDD becomes the blueprint for writing business logic in a microservice architecture, and it guides you to design sort of transactions that work in this architecture. And then not only that, this model exactly fits the capabilities of a NoSQL database where you do not have arbitrary transactions. And in fact, another term for some NoSQL databases is that they're called aggregate stores because, for instance, a MongoDB document would be an aggregate, and so a transaction which updates one aggregate would just update one MongoDB document. Likewise with a key value store. So you just follow these rules from DDD, and you have sort of business logic that works in a microservice architecture and with NoSQL databases. So it's quite fascinating. So that's aggregates. Incredibly useful tool for writing your business logic. So you just sort of, instead of thinking about traditional object-oriented design in terms of, let me go identify my classes and sort of have classes as kind of your unit of design, it now becomes, let me go and identify my aggregates, and then think about the behavior of the aggregates, and it's almost like the internal structure of your aggregates becomes secondary at that point. Okay, so that's aggregates. But in your system, you're still going to need some form of data consistency that spans aggregates or spans services. So going back to the credit limit, right, there is this rule that says, the open orders for a customer must not exceed the customer's credit limit. And as I showed earlier, in a monolithic system with a monolithic relational database, enforcing that is trivial. But now in this microservice architecture where different aggregates are in different services and in different databases, we have a problem. And as I mentioned earlier, you cannot use two-phase commit. And so the solution to this is to use what are known as sagas. And so a saga, it's almost, I forget the precise English meaning of saga, but it's like a long tale, right? Was it from Iceland or Vikings and stuff, right? They have sagas about epic battles and journeys and the like. So similar, in a sense, the similar concept. So it's like instead of a single distributed transaction that spans services or spans aggregates, you maintain consistency using these sagas, which are a sequence of local transactions, one in each service. And then the glue that binds, that results in a sequence of transactions are the events. So each service will execute a step of the saga, publish an event, which will then trigger another local transaction in some other service, or possibly actually within the same service as well if you wanted to sort of do it, kind of adhere to the rule of one aggregate per transaction in a strict sense. And so a distributed transaction gets replaced by this saga that is a sequence of steps. And the way this would work in the order processing example is as follows. So you've got the order service and the customer service. When a request to create an order comes in, it will actually create an order in a pending state. So that's the first local transaction, simply creates an order. It might do some simplistic validation, but it's not going to actually check the credit at this point. And then the order service will publish an event saying, I've created an order. The customer service will receive that event and then attempt to reserve the credit. So in this model, the customer is keeping track of which orders have used so much of the available credit limit, and it will attempt to reserve credit for this newly created order. And then the customer service will emit an event saying, an event that represents the outcome of the attempt to reserve credit. So either a credit reserved event or a credit check failed event. The order service is going to subscribe to those events, and when it receives one, it will either approve the order or reject it. So as you can see, we've got these two services. Each service executes a transaction that emits events that will then trigger another transaction in some service, which will then emit events that will trigger another step, and so on and so forth. So this is the way in which you maintain data consistency in a microservice architecture without using two-phase commit. And it's an eventually consistent model, because if there were no other updates, eventually all of the events will get processed and the data will become consistent. But on the one, and companies have been using this approach for some time. One classic example is eBay back in the sort of maybe 2006 timeframe, 2007 timeframe. They evolved to what would now be called a microservice architecture, and they had multiple databases, relational databases. And even though they were relational, they did not use distributed transactions, and they basically used an event-driven approach similar to this to ensure eventual consistency across their multiple databases. So it's sort of not a particularly new technique. Definitely has downsides, and one big downside is the need to write compensating transactions. So if you think about rollback when you're using ACID transactions, you can update or insert as many rows as you like, and then if you decide at some point that some business rule is violated, you simply roll back the transaction, and it's as if nothing has happened, right? And that's really simple in general, right? In a Saga model, you might have executed 10 steps, and each of those 10 steps has been a local transaction that has made changes to a database that have been committed, and then the 11th step fails for some reason. You then actually have to explicitly undo the first 10 steps. So in other words, you have to execute compensating transactions, possibly a sequence of 10 compensating transactions that undo what was done previously. So for instance, if you're transferring money from one account to another, you might debit the from account, and that gets committed, and then when you try and credit the to account, perhaps the to account is closed, and so you have to undo the debit by performing a credit at that point. Which is actually exactly how banks work, right? I mean, we kind of like to think of banks work by using a sort of ACID transactions, but they actually use a model that's much closer to the eventually consistent model I'm describing here. But it's more work on the part of the developer. You can't roll back, just execute a single rollback statement. You have to explicitly undo everything you've done, so there's a bunch of bookkeeping and so on. But obviously it's doable. And this is sort of reminiscent of some of that business workflow stuff as well, so it might also be familiar there. And there's also an interesting little technical challenge. In order for the Saga mechanism to work reliably, you have to be able to simultaneously update a database and publish an event. Those two things have to happen atomically. Because if you didn't, and let's say that you updated the database and committed the transaction and then crashed before publishing the event, your system would be in this permanently inconsistent state. We actually need sort of transactional semantics for both the database update and the publishing of the message. And the irony is that the traditional way to do that in a Java application is a distributed transaction involving your JMS message broker and your JDBC database. But that's exactly the kind of technology that we don't want to use, right? 2PC is not an option anymore. And it turns out there's actually a few different ways to do that, including using a database table as a temporary, as a message queue. So you can sort of update the order table and insert an event into a message table sort of /queue in your database, and then have another process that pulls that event out and publishes it to a message broker. And there's a few different mechanisms like that. And if you go to learnmicroservices.io, you will eventually find a description of the various options. But the one that sort of interests me the most right now is this approach known as event sourcing, which is, it's not exactly part of domain-driven design, but it's a technique that basically grew up, kind of was developed by that community. And the big idea with DDD is that, sort of crudely speaking, you basically use the events as your persistence mechanism. So there's no separate notion of updating a database and publishing an event. With event sourcing, all you do is save/publish an event to the event store. So two operations, which are tricky to make atomic, become one operation, which by definition is atomic. And so the way event sourcing works is that for every DDD aggregate, every domain object or business object in your system, you identify the domain events, the events that represent state changes. And there's this really fascinating technique called event storming that's a workshop where you have lots of colored Post-it notes and you brainstorm what are the events that occur in my problem domain. So it's worth Googling. And we did something like this at the local Jug a month ago, and it was an absolutely fascinating experience. But you basically figure out what are the state-changing events in my system. And so for an order, they would be the order was created, it was canceled, it was approved, it was rejected, it was shipped, it was delivered, it was returned, and so on and so forth. And then for every one of those events, you actually create event classes. So you treat the events as first-class citizens in your domain model. So that's sort of, that in itself is just sort of the idea of domain events from DDD. But then what event sourcing does, it actually uses those events as the persistence mechanism. So rather than mapping an order, a specific order to a row in an order table, which is the traditional way of persisting domain objects, instead, you just persist the events. So at least conceptually, you just have one table in your database, the events table. And so whenever a domain object gets created or updated, you insert a row for the corresponding event. So when an order is created, you would insert an order created row. When it's approved, you'd insert an order approved event. And then when it's shipped, you'd insert an order shipped event. And so it's these events that represent the state of your domain model. Sure, I got one quick question. That is yeah. So the question is this shared across the microservices? So the first thing to say is that this is just kind of a logical, kind of conceptual view of how the system would work. And that depending on how you've implemented the event store, there might not actually be any tables. But yeah, there's several models. You could have one event table for your entire system. You could have an event table per service, or you could have an event table per aggregate type. So this is really, just think of this as a conceptual table. So the idea is, yes, for every state change, you insert an event. And there is this order data column where I've just put ... But you could imagine that to be a blob of JSON that contains the additional data. So for an order created event, that would be all of the order line items and the like. For an order approved event, there might not actually be any additional data. Likewise for an order shipped event. Or maybe the order shipped event would have the tracking number as part of the event data. So that's the model. And so this is how you represent the state of orders in their entirety, and there's nothing else. And so in order to recreate an order, in the same way that JPA or Hibernate issues a bunch of selects and then merges all that data into an in-memory representation, in this system, you'd load the events for an aggregate and you would replay them to reconstruct the current state. From a functional programming point of view, you're doing a fold over the event stream to reconstruct the current state. So if you look at an aggregate, like here's the customer aggregate. It has some fields like the credit limit, credit reservations. It has a bunch, then the methods are somewhat different. There are process methods that take commands which represent requests to update the customer. And they actually yield a sequence of events. So those methods don't change the state of the customer. They give you the events that represent the state change. And those events will be persisted in the database. And then you have an apply method that takes an event and updates the state of the customer. So the sort of business logic's structured in a slightly different way. And it's all about being able to generate the events that represent state changes and then apply the events in order when you're replaying them. And then hopefully you can see this at the back. So this is the class. It extends a base class. And then you can see the process methods. This is the most interesting one because it's got some business logic. And it's processing a request to reserve credit. And it's saying if the available credit is greater than or equal to the order total, then return the customer credit reserved event. We've successfully reserved credit, so return an event that represents that state change. Otherwise, return a credit limit exceeded event, so we failed to reserve credit. And then there's the apply methods. And the corresponding one there is customer credit reserved event. For customer credit reserved event, just updates the hash map that maps order IDs to credit reservation amounts. So all of the business logic, like the conditional logic that implements the business rules, resides in the process methods. And then the apply events take the events which have already happened and simply perform the state change. So there's no possibility of them failing. So it's kind of a different programming model, but you can mechanically transform a traditional code into this pattern. And the flow in your system is when a request comes in to create an order, you load the events, say, for that order. You create a brand new order object using its default constructor. You apply the event, so you iterate through the events, calling the apply method. You then process the command, which gives you new events. You apply those events to update the order, and then you save the events in the event store. And you do this with optimistic locking. So if there were simultaneous attempts to update the same order, the first one would succeed, and the second one would get an optimistic locking failure, and you'd have to loop back and loop around and retry. So that's one part. So that looks like a database. And then the other part is this event store lets you subscribe. So the customer service would say subscribe to those events. And and when an event occurs, it would update the customer using the same mechanism I showed on the previous slide, which would generate more events, which would then presumably get consumed by the order service. And then there are also you can have arbitrary event handlers that get invoked. They can update materialized views. They could send out notifications and just sort of perform arbitrary things, like you could analyze the stream of events for monitoring purposes, for machine learning purposes, and so on. So that's the flow. It's all very, event-centric. And the event store itself, is a combination of a database and a message broker. So it's sort of a database because you can put events in, you can get events out by primary key, but then it's also like a message broker because you can subscribe to events. And like if you go look at the open source version of our product, we actually took MySQL and Kafka and kind of glued them together to form the event store. But there's other different ways to do that. So event sourcing, has a whole bunch of benefits. It solves the data consistency issues in a microservice architecture. If you step back and you think, well, we need to maintain consistency across our aggregates, well, we're going to do that using, by implementing those aggregates using event sourcing and then using those events to drive sagas that ensure eventual consistency. The event publishing is super useful because once you have that stream of events, you can do many different kinds of things. You can feed it into machine learning. You can feed it into a monitoring system. You can send notifications to users. So, when you get a text message saying that your flight is delayed, you can think of that corresponding directly to the state of an aggregate changing off in some system. In the some airline application. This approach generally eliminates the need for object relational mapping, which even though we've had Hibernate and JPA for a number of years, it's still not a perfectly solved problem. So with this approach, you're storing the events, which tend to have a much simpler structure. And so we just sort of kind of bypass this whole OR mapping issue. And then also, because every event, or every change in our system rather, results in an event object, we actually get two things out of that. We actually have an audit log that is guaranteed to be correct. Every change that is made by a user results in an event, and we can record the identity of the user in that event. And we've got this permanent record, which is quite different than the usual way of writing our business logic and then bolting auditing onto it as an afterthought. And then also, because we're preserving the history of every domain object, we've got the entire stream of events for every domain object. That actually means that we could go back in time and ask, what is the state of this domain object 2 weeks ago? We have that. You just replay events from the beginning of time up until 2 weeks ago, and you have the answer. If we wanted to do that in a traditional system, we'd have to bolt this on as sort of an afterthought. Whereas here, it's just this built-in capability. Definitely some downsides. The code looks different, so it means rewriting our application. But it's sort of something that can be done when you're embracing the microservice architecture. As you incrementally extract out pieces of your system and turn them into services, you can rewrite them to use event sourcing. There's obviously a learning curve, but it's something you just have to work with for a while. Also, the events, they never go away, which means that we've got this awesome audit log, but at the same time, we have to deal with the structure of our events evolving over time. We might add new attributes. We might add new event types. And because they never go away, our code might actually have to deal with multiple versions of the same event. And so it just requires some careful design. Also, because this is an event-driven system, we have to detect and ignore duplicate events. You know, our message broker might deliver the same event multiple times. So either our event handlers have to be idempotent, they have to sort of always do the same thing every time they're invoked with the same event, or you're going to have to write code that explicitly detects and discards duplicate events. But once again, I mean, like, some frameworks just have this built in, so it's no big deal. And even if you have to do this bookkeeping yourself, you know, like system I work on, every event has this ID that's monotonically increasing. And so you just keep track of the highest event ID you've seen and discard the older ones. So that bookkeeping is quite straightforward. But then there's another problem, which is that we're representing the event, the state of our domain objects as a series of events. And that is a format that is not very friendly to querying. So, you know, obviously we can find events by primary key. That's not a, you know, that obviously works, and fold them together in memory. But then let's imagine that you want to find all bank accounts whose balance is greater than some amount. In an event-sourced system, there isn't a balance column that you can just trivially write a where clause for. Because all you would have is a bunch of account debited, credited events. In theory, if you used a database that had JSON extensions, you could write a query that had like a nested select that did the folding of events, but it would become very complex. It would probably be quite inefficient. And then plus, some event stores only support primary key-based lookup. And so you can't write arbitrary queries. So the standard approach there is to use this other pattern, which is the subject of a whole other talk, and it's known as Command Query Responsibility Segregation, or CQRS, where it's basically a generalization of the technique where you might say use MySQL as your system of record, but then you'd use Elasticsearch for doing text searches, and you keep them in sync. Well, in CQRS, you define these view databases specifically to support your queries. And then those view databases are kept up to date by subscribing to the stream of events that come out of your event store. So that's an approach that people will use. And it turns out that it actually tends to be really, really useful to have these denormalized representations of your data because they directly support very sort of scalable, very efficient queries. So it's more complexity, but it's generally worthwhile. And I notice I'm running out of time, so I think I'm going to skip over this topic because it will make everyone's head hurt explaining all these details. Whoops. I encourage you to go read this online because it's some super useful stuff, though. But just with the interest of finishing on time, I just want to say, so sort of in summary, right? Like aggregates, really you should think of those as the building blocks for your microservices. And at a higher level, it's like go read Eric Evans' book. It's not necessarily the most accessible book, but the ideas in there, both of like the building blocks, like aggregates and entities and value objects, are hugely powerful. But the concepts of bounded context as well, incredibly useful when you're developing applications with the microservice architecture. And then you want to use event-driven sagas to maintain data consistency. I think that approach is going to be used more and more as more and more business applications are written using the microservice architecture. And then event sourcing is an excellent approach to implement, to actually sort of as the means to generate the events that cause the sagas to flow. So that's my talk. Thanks for listening, and I hope that you found it useful. And here's a whole bunch of contact information. So thank you.